This is what we are having. We know that this is a MOSFET. Actually, we'll actually get to know, okay, how do we actually fabricate this MOSFET. Maybe if you can remember the way how we used to write a MOSFET in the cross-section view is, so you're going to have the gate oxide, over which you're going to have a gate structure, and here you're going to have the source drain. So if it is P minus substrate, so you will have n plus as the source and drains. This can be source, this can be drain. You have this as MOS, this is gate structure. Now depending on what you want to construct, whether you want to construct an amplifier or you want to construct a digital circuit, we're going to use it. So this is how the 3D what is that cross section view looks like. The 3D view of this would be something like this. So you can have it as something like this. So this will going to run throughout the entire length. This is going to run throughout the entire length. This is there. This is there. You have this is the 3D view of it. This happens to be the width of the transistor, and this happens to be the length of the transistor. This is the length of the transistor. This is how a transistor is fabricated. In this microwind, you can do all these things. So you can able to diffuse a source, you can have a diffusion of the drain, you can have the gate of specified length, you can have a transistor of required dimension. So these are the things that are possible in this microwind software, which is I was supposed to say here. You can see fabrication of MOS and realization of I was about to type this digital circuits. This is you can able to realize any digital circuits. Of course, we will be actually learning how to write the digital circuit using MOSFETs. So it can be any Boolean expression. You give me any Boolean expression, whether it is half adder, full adder, maybe a mux, maybe a decoder, encoder. You just name any digital circuit, we can able to realize it using the MOSFETs. And then once it is written, when the circuit is written, you are supposed to write a layout the way how I wrote it over here. So what I'll do is let me just share both of them. Okay, this is how I usually do it. So what we'll do is we will actually show this as well as this simultaneously, so that you can able to make out. So now you can see I'm doing it now. Is this fine? Something like this, making you people to make this also visible, this also visible. Is this fine? Prithvish, are you there with me? Oh, 1 second.
Yes, sir.
Here it is a what is that camera sheet, and this is, suppose if at all if I'm using some textbook or some PPTs, so it is one-to-one relation what we'll be focusing on. Suppose if something is there over here, I can able to relate it to the board like thing what is written over here. Is that fine, Prithvish? You can be
Yes, sir.
you unmute the
Many,
entire session, so no need to mute yourself. You
okay, sir.
could not zoom. No, I can't zoom in.
Sir,
Maybe what you can do is, I
minimize
come.
PPT, minimize, sir.
No, I will do that.
Minimize the PPT. Sir.
Sometimes what happens is I may have to say, I may have to show both of them. In such case, I'll because if I want to relate this and this, then I'll be using both of them. If at all if I'm referring to only the what is that board, or like the PPT, which is, sorry, not the PPT, the camera one, then I'll just make it something like this. So we can just, okay, if you're not comfortable with that, okay, dual window, we can just make it single window so that you are all comfortable. Trying to enlarge, this is fine. No, I don't, okay, I cannot able to enlarge this. Is this not visible, Prithvish? Somebody
Visible,
says,
sir.
okay, try to enlarge. I think you can able to enlarge in your phone. You can able to enlarge. Suppose if you are looking
Yes,
at,
sir.
okay, you can just
We can
enlarge it and
enlarge
then see.
it.
I think you can able to manage it, because if I start enlarging this, then if I write something over here, then I need to keep on zooming it. So we will ensure that, okay, entire page is visible to you people, so that I can able to write from here to here in a single stretch. So I won't usually zoom it. if you are assume that okay, if I'm writing over here, maybe in your mobile phone you can able to zoom that particular portion if you want to specifically look into. And what all thing that I'm writing over here will be recorded, so it will be sent immediately after the class. Of course, this will also get it immediately after the class. That's how it happens in my regular classes. Okay, let us move on to this. What all thing you'll be doing here is once you are done with realization of digital circuit, then you'll be writing the layout for the circuit. Of course, when you're writing layout, there are some rules to be followed. So that is called lambda based rules. We'll get into what are these rules and then why we are supposed to follow these rules. Because when you're there traveling, when you're driving any vehicle, you have to follow some traffic rules. So traffic rules are ensured that okay, you can drive safely. You have to always go on the left hand side, left. You cannot overtake on the right side, okay, left side, all those things. Now there are some rules for each and everything. Even for layouts also you have some rules which we call it as lambda based rules. And then of course quantitatively analyze the CMOS circuits. So here we are not doing any qualitative analysis, meaning that you will not be deriving too many equations, but you will quantitatively analyze okay, all the CMOS circuits. When I say CMOS circuit, there are various CMOS circuits that you will be studying. It will be static CMOS, it will be dynamic CMOS, it will be pseudo NMOS, it will be pass transistors. Different type of CMOS circuits will be used in realizing any digital circuits. Then of course we'll also spend time in what is the impact of sizing of MOSFETs on the performance of the entire system. And then we have of course this is very interesting. So as I was talking about, you can design any digital circuit. It need not be combinational one, it can be sequential also. uh, Prithvish, can you just name some sequential circuits? Prithvish?
Sequential.
Mm-hmm. Sequential circuits. You're there in that digital VLSI design also, no? There Rajabandi
Yes,
sir
yes,
designed some sequential circuits using 3 idiots. Forgot?
yes.
Anybody can just open and then start saying okay, sequential circuits.
Some mux, flip-flop.
Mux is a sequential circuit. Mux, okay, where is the clock for mux?
Counters.
It is counters. Anything that involves what is that? Flip-flops. Is it not? So counter involves flip-flops. It's a sequential circuit where the output depends on the previous state and the present state. So there should be some memory element in that. So that's your sequential circuit. We will be actually seeing okay how to design it. It is not only a mux. How do you design using these layouts? Because as I wrote here, for a simple transistor, so many drain source, all those are required. So if it is a sequential circuit, how do you design it? How do you design? And we'll also spend a lot of time with memory concepts. It can be ROM, RAM, it can be EPROM, it can be different types of flash memories and all those things. So we'll be spending quite amount of time with the memories that is required for any digital circuit. Okay, coming to Moore's law. This is very essential. Whoever starts studying VLSI, the first and foremost thing that will be asked is Moore's law. Define what is Moore's law. Of course, it is not at the level of engineering, that is at UG level we ask what is Moore's law. So just to inform you that maybe 15 days or 10 days back we had the interview of faculty for the faculty post. We had the interview. Even in that case, okay, we asked okay, one of the candidate has finished actually his MTech in VLSI and embedded systems. The first and foremost question from an expert was, can you define Moore's law? Because Moore's law is so essential or so fundamental that if you have studied VLSI means you should know what is Moore's law. That's why you can see the first technical content of this particular VLSI is Moore's law. Moore's law states that, of course, it states that the number of devices, when I say number of devices, number of transistors in a chip of given area doubles for every 18 months. So if I just take the example, okay, what I'll do, I'll just open the Okay, I just open this camera, and then if I just take this is the area of a particular semiconductor. In this area, assume that you had x number of transistors. X can be 10,000, it can be 1 million, it can be 1 billion. After 18 months, after 18 months or 2 years, so that there is a okay, it's an understanding that either it can be 18 months or 2 years, even though there's a difference of almost 6 months, but sometimes they call it as 18 months or sometimes they call it as 2 years. Both are valid. What does Moore's law says is, in a given area of semiconductor, the number of transistors in this particular area doubles for every 18 months. After 18 months, the process technology has improved in such a way that you can able to suppose that you are accommodating around 1000 transistors over here. After 2 years, what happens is the technology has developed to such an extent that in the same area I can able to place 2000 transistors in the same area. Getting the point? So how does this is happening? This is happening because of improvement in the process technology, improvement in the devices. There can be a lot of what contributions that are going into increasing this number of transistors in the given area. In just 18 months it is doubling. Don't think that okay, this number of transistors will simply become double the same one. It is not that. Given area, suppose today if you are if you can able to put only 1000 transistor, maybe after 2 years the technology has what improved in such a way that you can able to put 2000 transistor. This is a time gap of 18 months or 2 years. Prithvish, can you what did you understand from this? Could you able to get what is
Sir,
Moore's law is?
yes, sir. Are they relating to technology, the rate of technology, sir, or what we
Exactly.
could
No, the
represent?
technology is improving such a way that now you are making everything compact. So you are reducing the sizes so that you can able to accommodate more and more number of what functionality into a given area. If you can just remember
Yes,
the what laptops maybe 5 years back and the laptop size now, can you see how much it has shrunken? How much it has
yes,
reduced?
sir.
It is purely because of these advancements in the entire process of manufacturing of the VLSI, the manufacturing of devices, which is a VLSI industry. So that's what. Can you see here? This graph shows. I think this is visible now. Fine. Okay. What does this graph shows is just have a look at the starting year 1960, because even though the transistor was found in what is that 1949, the first IC started in 1960. You can see the number of transistor is only one, that is IC version, and you can see this is year. Can you see the graph here? Now you can see this is actually 2010. The number of transistor per die is a standard dimension. Per die you have 10 to the power of 10 transistors per die at the end of 2010. Can you just see here, sometimes graph is steeper, sometimes the graph is of course not that much steeper. Can you make out that, Prithvish?
Yes, sir.
Can you see here, sometimes it is sharper,
Yes,
sometimes
sir.
sharper matlab it is steeper, and then it just slope reduces, it is increasing. These all things are happening because suppose assume that okay, now it has become flat. Why it has become flat is there are no much development happening during that period, so that's why it is slightly flattened. You can see immediately they found out something, the rate of increment has increased, and you can see it's almost flat here. Can you see here, this is almost flat.
Yes, sir.
It actually means that during that period they could not achieve too much of technology development, that's why it is flat. But you can see here this is so steep. So there would have been a breakthrough in some of the technology. So that's why the number of transistors has increased from 16 million to 64 million. Can you see the what jump in number of transistors per die size? This is how.
Yes, sir.
This is not a linear graph. This is not a linear graph. So coming to what latest years, now you can see it's almost becoming saturated. It's not increasing at a rate how it was increasing in the earlier case because of a lot of limitations. And of course it is also saying that uh, depending on what type of you can see in 1975 projection it was supposed to go this way. So you can see the projection was this and the actual achievement is this. You can see we have different colored lines. One is, you can see this is red, which is corresponding to memory, and this is for microprocessor.
Microphone.
Microprocessor, you cannot achieve that much density as that of memory because memory doesn't require a complicated circuit. Whereas for what microprocessors, you need to have so many other connections also. That's why you cannot achieve to that much extent. This is the expectation. This is the memory achievement. This is the processor achievement. You can see that's what is the difference here. You could not still achieve the way how you are mostly expected, but it is certainly moving in that direction. Let us move on to the next slide, which is almost similar to the previous one, but here it is much more specifically given what is the number of transistors. You can see it is, and you can see the frequency also they are talking about, and they are also talking about the typical power dissipation. Can you just imagine the amount of power that is dissipated, Prithvish? Just see what is the power. Uh, those of you have
Oh,
laptops, suppose if you have your laptops on your lap for longer time, will you feel it's very hot?
no, it's
It will not be
increased, sir.
hotter. No,
Yes,
assume that okay. If you just hold your hand near that fan, which is rotating
yes,
so
sir.
fast, can you just feel the heat?
Yes, sir.
Because that is actually taking out the heat. If you can just imagine what is the amount of power that is being dissipated maybe around this year 2020 or 2018, can you see what is the amount of power here, Prithvish?
Yes, sir.
How
Yes,
much the
sir.
power?
10 power 2
Right,
means 100 watts.
100 watt. Can you just imagine a 100 watt bulb
100
running?
watts per.
Of course, per that per die.
Yes,
Per die. It's
yes,
like okay, 100 watt is too much. 100 watt, okay, it's actually equivalent to a 100 watt bulb dissipating that much amount of heat. So that's why you can see when you put your hand very close to that okay, what are that cooling fans, so they'll be so hot because unless you take out the heat, the transistors uh, cannot able to withstand that much amount of heat. Can you see the what that frequency here? What is the
yes,
frequency
sir.
of operation here? Can you just predict?
10 1000 kilo,
10
1000
power 3,
megahertz.
10 power 3 into megahertz, close to
Yes, sir. Giga.
gigahertz. So
Gigahertz.
those of you bought a new laptops, can you see what is the frequency? 3 gigahertz, 5 gigahertz, 10 gigahertz. Can you see they are almost at that range? This is
Yes,
10
sir.
gigahertz. This is 1 gigahertz. This is 10 gigahertz in terms of gigahertz here. So can you see this is almost close to 5 gigahertz or 6 gigahertz? Now
Yes,
this is
sir.
how the frequency wise you can see it's almost flattened here. It is almost flattened, even though you can able to have more and more transistors, but the frequency you cannot achieve to that extent, that rate. You can see it's almost flattened from almost you can see there is a slight variation. There's no huge change as it is in terms of the rate of increment of this frequency is limited because of so many reasons. Of course we can able to certainly look into those areas, okay, why it has almost flattened here. Okay, let us have a look at this slide. Can you just read this, Prithvish? This bottom one.
Yes, sir. The
Hmm.
price per transistor
Hmm.
on a chip has dropped dramatically since Intel was founded in 1968.
Hmm.
Some people estimate that the price of transistor is now about the same as that of one printed newspaper character.
Oh, what does it mean? Assume that this is a printed newspaper. You want to, of course, if you want to print any letter, you need to spend some money. No, assume that I want to print this T letter. The amount of
Yes,
money that is required to print this T is equivalent to making a transistor.
one transistor.
One
Yes,
transistor. It is so cheap. Meaning, suppose if you just go in terms of 1 to 1, because in a laptop you're going to have billions of transistors. That's why it will cost around 50,000, 60,000 or 40,000. Because suppose if you just boil down to single transistors cost will be almost close to printing one letter in a newspaper. It is so cheap. Suppose if you take in terms of transistor, but a single transistor is of no use. You need to put it in the circuit so that it can be n number of transistors. It can be million or it can be billion transistors, so that you can able to see your mobile phone or a laptop which can work as per your instructions. Oh, this one. Can you see here? This is interesting.
Yes, sir.
Can you see here at the bottom? At the bottom, you have two different colors. Maybe one is NMOS, other is PMOS. Can you see? Over that, you have these stacked lines. These are all called as metal layers. Because in the previous thing we have seen that there are so many number of transistors that are there. Assume that. Okay, now let me just take into this particular. Okay, not this. Okay, let me just take this. Suppose if I have one transistor here, if I have one more transistor, if I have n number of transistors. Suppose if I want to connect this to this and this to, okay, assume that I have one more transistor here. Now I need to connect this to this transistor. Can you see this is got shorted? Hello.
Sir.
Hello.
Yes, sir.
Can you see this got shorted? In such case, what they'll do is, it is not possible to do it in a single layer. Have you seen PCBs? Single sided PCB, double sided PCB? Heard of it?
No, sir.
No. Single sided PCB, nobody? Diploma students?
Yes, sir.
What do you mean by single sided, double sided? When do you go for single sided? When do you go for double sided?
So when the complication is more,
When number of connections to be made across the components is more and more, you cannot do it in a single layer. If you start doing it in a single layer, you may have to have jumpers. In such case, you'll go for 2-layer. If the circuit is much more complex, you'll go for 3-layer, 4-layer, or multi-layer PCB. Correct? Hello.
Yes.
Yeah.
Yes, sir.
In such case, since the number of transistors are huge in number, the number of metal layers required for interconnection will be now at this point of time 12 layers, 1, 2. So you need to have 12 different layers of metal to have the connection among the circuits which is there at the bottommost. So at the bottommost you have millions of transistors or billions of transistors. They have to be interconnected properly as per your requirement. So if you want to make the connection, you need to have metal lines. So if you want to have metal lines, you need to have n number of metal lines. So that n is almost 12 in number. So you're going to have 12 different layers. Would you be able to get, okay, all of you, what do you mean by this 12 different layers? We call it as intermediate layer, semi-global, and then global layers, depending on what is the functionality of those signals. Assume that does all the circuit require VCC? Hello, Prithvish?
Yes, sir.
Does all the circuit require supply voltage?
No, sir.
No. Assume that you have so many transistors. Most of the circuit require VCC. Correct?
Yes, sir. Yes, sir.
So, because without VCC they cannot work. No, you need to have VCC and ground. So those we call it as supply rails. So you can see. Let me call it as, those are called as supply rails. So heard of this railway track? This is that
Yes,
rail.
sir.
This is the trail. So you will have a rail of plus VCC running. You'll have a rail of minus VCC running or ground running. You will have a lot of circuit here. You drop a line here. You drop a line here. You take a line one. This. Can you see? Most of the circuits require this supply. Correct?
Yes, sir. Yes, sir.
We call them as global lines because they are globally required for all the circuits.
Yes, sir.
So if you can see here, Can you see this is some global, semi-global, and intermediate? Intermediate, of course, they may be specifically required for the adjacent components. Semi-global, something maybe clock is required for some part of the circuit. It is not required for some other component, some other part of the circuit. So depending on what is required, whether it is globally required, whether it is not that much required, you just put them in global level, semi-global, or intermediate level. Okay, this is a typical transistor, how it looks. Can you see this? I actually wrote in that sheet. This is actually an inverter. Suppose if you give 1, this is a digital circuit. If you give 1 as the input, the output will be 0. Or if you give a 0 as the input, the output will be VCC.
Wow.
So this is how a CMOS inverter looks like. So this is looking so scary, no? Is it?
Mhm.
Scary, no? Is it looking so scary? Circuit.
No, sir, but we could not understand
Of course,
how
it
it
looks okay.
is.
Some blocks are there, n plus so many things are there. It is not
Yes,
scary. It is very easy to write it. So it will be a left-hand job once you get to know what is the CMOS fabrication is. This is how a fabrication process is carried out. This is called as yellow room, where you can able to where all the. Can you see how clean this is?
yes, sir.
Can you see the cleanliness of this one? Of course, maybe once you people come down to SIT, so I will take you to clean room that is there at SIT, so that you can able to witness similar type of experience. Can you see that person wearing a gown with this hands are covered with gloves, so that you are not supposed to operate with bare hand. So because bare hand will have a lot of contamination, so it should be contamination free. These are all clean rooms. And this is the wafer. Wafer is one where across using which you can able to make the devices. You can see this is a wafer that it will be cut, and then finally you are actually transferring that pattern onto this wafer. I think I have shown you the PCB that I have made in the previous semester. Could you able to see? Could you able to remember that? I just showed you a small piece of wafer where you can able to see that small dots. Could you remember? Did I share that? Hello.
No, sir. No, sir, you didn't share.
Okay, maybe let me just show some other time. Okay, this is photolithography used to transfer the mask onto that. What is that wafer? Finally, you'll have this. This is a This is a die of almost. What may the dimension of this? Is it 12 inch? Will it look like 12 inch?
Yes, sir.
This is almost 12 inch. 1
Diameter.
feet is there. 1 feet is there. So in order to make this, it takes more than a month time. More than a month time to process this entire thing. Okay, this is a very brief introduction of, okay, if you can able to understand what this is, then I think, okay, I could able to make you people understand what is VLSI is, and then if you can able to identify each and every what component of this particular what. So if you can able to understand what is this UV light, what is this clean room, what is this mask, what is this what is this pattern. You can see there is a photoresist is there, there is a wafer, you can see that pattern has been followed this. If you can able to understand all these things, then you can able to comfortably place yourself in a better position when you are answering the questions of any interviews. Coming to exact syllabus, what you have, I don't have much time now. I think since I started 5 minutes late, let me just take not more than 1 more minute to just show you that where is my, okay, this is can you see this now?
Same. No, sir. Ah, sir, now we can
Now it's
see.
visible. So this is
Yes, sir.
digital VLSI design. I'll share it in the group. Okay, this is a 3 credit course, weekly 3 hours, and of course it is 50 marks for both CIE as well as CE. Issues and challenges in digital IC designs. You can see there is a Moore's law and design styles of VLSI, MOSFET fabrication, basic steps of fabrication. You can see CMOS P-well, N-well process, design rules, that is lambda based rules. Then comes the CMOS inverter, okay, how do you actually fabricate inverter? So what are the issues involved in finding out the propagation delay, parasitic capacitance, and all those things. Then comes one module with full of what combinational logic circuit design. Next comes of course combinational plus sequential circuits. Next is arithmetic block, where you can able to find out, okay, how to do the design of adders. It can be what carry lookup adder, it can be carry bypass adder, different types of adders, and of course even we'll also look into the multipliers here, and of course semiconductor memories, as I said, DRAM, SRAM, of course the testing of VLSI circuits. Okay, once you make the VLSI devices, unless you test it, nobody will accept, okay, for the process. No, they have to be tested. And this is a textbook which we'll be referring. So this is Rabe textbook. Of course we call it as JM Rabe. So I will share the soft copy of this in the Moodle platform. So I'll be creating a Moodle platform with you people. Of course we have these reference books, so which you can certainly refer, but basically we'll be concentrating on this textbook, that is JM Rabe. Okay, that's it for the day. So we will see in the next class. So we'll actually going to start with CMOS inverters. How do we realize a CMOS inverter, and how do we start realizing any given Boolean expression using CMOS circuits. Thank you so much for being with us for almost 45 minutes. So we'll see you in the next class. Before you just log out, let me just take the attendance over here. I'll scroll through that thing. It is not taking too much time. Okay, it is now recorded. You can now leave. Thank you so much.